Okay, so we're gonna briefly turn into like a chemistry class more than physics has been recently. Because the next two units we're gonna be looking at are both looking at things that you probably went over when you were in Jennings' physics class. First of them being the unit that we're on right now, that being thermal physics. So like talking about temperature and changes in states of matter. Okay, so I'm sure you remember the states of matter, right? You got solid, liquid, gas, and plasma, but we're not going to talk about that one. Okay, so with a solid, it's got a defined shape because the individual particles are stuck together in a lattice structure. As it heats up, those bonds between molecules start to break. With liquids, they're still largely connected together, but they are able to flow around a little bit more. That's what allows a liquid to change its shape to fit whatever container you put it into. A gas, those bonds between molecules are completely broken, and now the particles are free to move around their vessel as they will. Also, as you're increasing the amount of energy that you're adding, as you're going from solid to liquid to gas, they're moving faster. Okay? They're getting hotter. All right, so if we were to make a graph looking at the temperature changing here, okay, if we had a better marker, and a graph with temperature on one axis and time on the other. Let's say that we're heating this thing up at a constant rate. Okay, let's say that we're looking at ice. Okay, so if this thing is temperature in degrees Celsius, all right, then right at 0, that's where ice, melts, turns into water. So let's start it below that. Let's say that we're starting with a piece of ice that is below freezing when we're starting. Okay, as you add heat to it, as you allow this thing to be given energy, it is going to be increasing in temperature. It'll be doing so at a constant rate. Okay, but right when it gets to 0, and this will happen to anything changing between states, it's going to do something weird, right? If we were measuring that, and we probably will do a lab with this, I don't see why not. When it hits that 0 mark, it stops changing temperature. For a while at least, while it melts. Okay? And while it's doing this, you're still adding energy, but the temperature is staying constant. Basically what's happening here is it's using that energy to, instead of raising temperature, change the distance between particles, separate some stuff, break bonds between molecules. Okay? So if you're actually melting it down ice, you'll see that little flat point there, and we're going to be doing that. Okay? Then, after that, once you have melted all of the ice down into water, liquid H2O, then as you add heat, it will begin to rise again. Okay? Up until it hits 100 degrees Celsius. Okay? At that point, it will again stop changing temperature. For as long as it takes to boil, it will flatten back out again. Okay? And this point is going to be a lot more time. Like if you're looking at the time it takes to turn from ice to a liquid, as the time it takes to go from a liquid to a gas, this is going to take a lot more time. The reason for that is because it takes a lot more energy to separate it, right? Because when you're looking at going from a solid to a liquid, in a liquid, yeah, there are less bonds between molecules, but they're still bonded to each other, right? You don't have to separate every single molecule of water from every other molecule of water to turn it into a liquid. To turn it into a gas, though, they're all free from each other. Steam, when you're looking at a gas, they're free to move around. You have to break every bond. Okay, so it's going to take a lot more energy there to turn it into a gas. Okay, and then once it's a gas, then it will begin to raise in temperature again. Okay, so this section, this is where you've got your solid. This section, this is where you've got your liquid. And this section, this is where you've got your gas. All right, but those intermediate points, that's where you've got a transition. Okay, so this is where it is condensing or vaporizing. Okay, vaporizing going from liquid to gas, condensing going from gas to liquid, because the exact same sort of shape forms if you were cooling something. You would just be going in the opposite direction. And then this section here, this is where you've got it melting or freezing, depending on which direction you're going. Okay? And each individual thing that you're heating up will follow a different sort of path up, but the general structure will be the same. You'll have a slope when it's a single state of matter, as it's going between those, and then you'll have it flattening out when it's actually going through a transition. Okay, so this is our general heating curve. Okay, next thing on our notes, talking about evaporation. All right, so if you're looking at this graph, right, you got to heat something up a significant amount to get it to go from a liquid to a gas if you're planning on doing it based on temperature alone. Okay, but you can also just like have a cup of water sitting out on a table. Give it a few days, cup of water's empty. It didn't like heat up to 100 degrees Celsius while you weren't looking, but still all the water's gone. Okay, so how did it turn from a liquid to a gas? Okay, so evaporation, geez, is kind of an interesting case where you're not looking at temperature change so much as just like the average temperature. Okay, because if you've got a glass at room temperature, the whole thing is going to be about, what is it, 22, 25 degrees Celsius. I can't remember which one was it. 24. Let's say 24. Let's say the whole thing on average is 24 degrees Celsius. Okay, but that's an average. Not all of the particles are going to seem to be the same temperature. Okay, you'll have some that are going slower and sticking around. All right, you'll have some that are going faster and might even be fast enough to get a little hop. Okay, because they're all moving. They aren't all connected together. So some of them might be up a little bit. And the ones that go back to the water, well, they'll stay in the water, right? But some of them, right, you're looking at an average temperature. Some of them will be significantly hotter than others. They'll be moving significantly faster. The ones that escape, well, those are the ones that turn into a gas. Okay, so these turn back into water, and these turn into gas. You give it enough time, there's your water, it's gone. Eventually, just taking ambient temperature from around them, you're going to get some that are hot enough to leave. Okay, give that enough time, eventually you'll run out of stuff in the cup. Okay, that's why, like, if you get like damp and the water is evaporating away from you, you feel cold. Right? The reason for that is because if you're looking at all these molecules here, the hot ones are leaving. They're turning into a gas. Okay, so you're left with the ones that have below average temperature. That's why you feel cold as you're drying off. Same thing happens if you do it with like isopropyl alcohol, which evaporates very quickly. Right? It feels cold. The isopropyl alcohol started off at room temperature, like it was just sitting in a bottle at room temperature for hours and days and months at a time. It's at room temperature, but it feels cold as it evaporates away from you because the stuff that has above average temperature is leaving. Okay, so with evaporation, it's still based on temperature, what's making it turn from a liquid to a gas. It's just that not every particle there is going to have the same temperature. On average, they have a temperature of room temperature. Some of them are going to be hot enough to escape. And you're left with the ones that aren't, which will then take in energy from their environment, go back to room temperature, and it's a vicious cycle of eventually just all evaporating away, okay, until it condenses somewhere else that's colder. Okay, so now when we're talking about temperature on that graph there, we did put it in Celsius. Okay, so Celsius, it's okay as a unit, right? Like it's really useful for chemistry because if you're looking at Celsius, you've got boiling at 100 degrees, and you've got freezing at 0. All right, which is great because most chemistry is about water. But that's very specific, right? It's just about water, and it's just about water in particular circumstances. Like you look at salt water, it has a different boiling and freezing point. Okay, so we need pure water. Not only that, we need pure water at 1 atmosphere of pressure. Okay, we're looking at water at sea level on Earth. Okay, because if you take it to a different altitude where there's a different atmospheric pressure, it's going to boil at a different temperature. Like it's noticeably different. If you try and boil water in Flagstaff, it's a different temperature than if you try and boil it at San Diego. I don't know, something on the sea level. Okay, so pressure makes a difference. The purity of the water makes a difference. So this isn't a great way to structure all of our ideas of temperature as a scale, because even water isn't even consistent. Okay, so we need something that works for everything. All right, so we want something that starts at 0. All right, if we're thinking about temperature, thinking about that graph there, the hotter it got, the faster it was moving. Okay, and as we remove energy, it's going slower. Right? There's a flat limit to how slow something can move. Not moving at all would be the lowest speed, right? Because if you're moving in the negative direction, well, that's still moving. Like if you're looking at kinetic energy, how much energy you have in something's motion, there's a v squared there. If you're going in the positive or negative direction, the sign gets canceled out. Okay, so the absolute lowest temperature needs to be where something doesn't move at all, and I'm sure you know what I'm getting at. We're looking at Kelvin. Okay, where 0 is absolute 0. Okay, so 0 Kelvin is the absolute lowest temperature. There is no negative Kelvin because it's already not moving. You can't have negative motion. Like negative motion is still just motion. All right, so Kelvin, we put 0 at absolute 0. So our conversion there, if you need to get from Kelvin, if you need to get to Kelvin, just take your degrees in Celsius and add 273. Every degree you go up in Celsius is a degree up in Kelvin. It's just they start them at different points. Right? Kelvin starts at the absolute lowest point. That's where it puts 0. And Celsius puts 0 273 degrees higher, where water freezes. Where water freezes at normal atmospheric pressure and with pure water. Okay? If you want to go the opposite direction, well, that's just moving around an equation. I'm sure that you can handle that. Just subtract 273 from your Kelvin to find your degrees in Celsius. Okay? So whenever we're doing calculations with temperature, do make sure that you're in Kelvin, because if you don't, if there's any sort of like division or multiplication, Celsius is just kind of like an arbitrary number. It's not going to work out with the math. Okay? So make sure that you turn it into Kelvin first. Unless, of course, we're looking at change in temperature, then you can get away with not converting it, because a change of 10 degrees Kelvin is also a change of 10 degrees Celsius. They follow the same scale, they just put 0 at different points. Okay, so we've got our temperature units. Next thing, specific heat capacity. I'm going to leave that little graph up there. Okay, because looking at that graph, as we're adding energy during these 3 points, our temperature is going up. Okay, and depending on what material you're looking at, that temperature is going to increase at a different rate. All right, if you've got metal, it changes its temperature quickly. It has what we call a low specific heat capacity, meaning that it doesn't take a ton of energy to change temperature. If you look at the table on the back of these notes, like if we compare aluminum to water, okay, that C there, that's what represents specific heat capacity. The smaller that number is, the more quickly something will change temperature. It will take less energy to change its temperature by some amount, okay? So like water, 4,180. It's the biggest thing on there. It takes a lot of energy to heat up water. You may have noticed that if you go to the beach, okay? You go there, like, honestly, barely after the morning. The sand is already super hot. The water is freezing cold all day. Doesn't matter how hot it is outside, that water is going to feel cold, okay? But it's been out there the same amount of time as the sand has. Why isn't it warmer? Water takes more energy to get it to change temperature. It just has a higher specific heat capacity, okay? So if we're looking at specific heat capacity, it's based on how much energy you got, okay? So the energy that you're adding, we're gonna use a Q for heat, okay? And this is energy, all right? So it's gonna be measured in the same units as energy any other time we talk about energy. It's gonna be measured in joules, okay? So that Q there, that heat, is directly proportional to the specific heat capacity of something. The larger that specific heat capacity is, the more heat it's going to take. Okay? So the symbol that we use for specific heat capacity is a C for the capacity part. Okay? So this is specific heat capacity. Specific And another thing that's proportional to is the mass, right? If you've got a milliliter of water versus a liter of water, it's going to take a lot more energy to heat up the liter of water. The more mass you have, the more energy it takes, okay? So let's throw mass in there as well. cm, mass, measured in kilograms, okay? The other part of this is how much you want to change the temperature by. If you want to change it by a degree versus 100 degrees, changing the temperature by 100 degrees is going to take more energy, okay? So again, heat is going to be directly proportional to your change in temperature. The more heat you add, the more temperature change you get, okay? So then we're going to have a delta T, change in temperature. Okay, and that temperature there being measured in Kelvin. Now worth noting, we do have delta T there, change in temperature. Whatever your change is in Celsius will also be your change in Kelvin. So if you're strictly using delta T and you don't need to find like your initial temperature or your final temperature, you could use temperatures in Celsius and be perfectly fine, okay? But just in general, you want to convert from Celsius to Kelvin because there are other calculations that aren't going to be looking at just the change, it'll be looking at what is the absolute temperature at a particular time, okay? So I would suggest always switching over to Celsius, or always switching over to Kelvin from Celsius, but in this particular instance, delta T, your change in temperature, it could be either. It could be either Celsius or Kelvin, okay? But if we're looking at our units of specific heat capacity, well, we need to end up getting joules, and we don't have joules anywhere in here, okay? So specific heat capacity measured in joules, and we're multiplying by kilograms in Kelvin, so we need to be canceling those out with these units. So specific heat capacity measured in joules per kilogram Kelvin, okay? And you may see, if you like look up specific heat capacities online, you might occasionally see these in like kilojoules per kilogram Kelvin or kilojoules per kilogram Celsius, or you might even find them like joules per kilogram Fahrenheit, but gross, disgusting. Worth noting, if we look into the physics book, it does use different notation, kind of like how they use a U instead of VI and an S instead of displacement, or instead of an X for displacement. They do use slightly different letters. C they keep the same, M they keep the same. They use an E for energy, which honestly makes more sense, but I'm used to using a Q. I've always seen a Q used for heat. Why is it a Q? I have no idea, but I use a Q. Q. Also, they use a theta for T in the book, which is weird. So the way that they write it in the book is instead C equals M delta theta. No, that's not a theta, that's another T. See, I can't even get a theta out here. Delta theta? You got two Greek letters in a row. It looks weird. Anyway, but that's how they write this equation inside the book. It's the same thing though. C is still your specific heat capacity. The larger it is, the more energy you need to heat something up. Mass still measured in kilograms. Delta T. They just use a theta for it because I guess they hate T's for some reason. I don't know. They use a T at other points of the book. Why does it need to be a theta there? Gross. And then they use an E instead of a Q, which is honestly a good decision, but I refuse to abide by it. All right. So if we're looking at these specific heat capacities here, basically the larger the number is, the more energy you need. Okay. And don't worry about putting these on a note card. If you ever need any of them, I'll get them to you. Cool? Remembering to edit this out because I did just forget what the formula is. I think it's just ml. Is it ml? Yo, UML? Mole? Mole, 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 mole? 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 Yeah. Okay. Now, this is specifically for the points where it's changing temperature, okay? But we're also adding energy while it's staying flat, while it's separating out the particles. So we've got to have a thing for finding these two sections, the flat sections as well, okay? Now there's no delta T in there, okay? So it's not going to be proportional to your change in temperature, but mass still makes a difference, right? The larger the mass is, the more energy you need to add to get it to change from one state of matter to another. Okay? So, instead of specific heat capacity, we're going to be looking at latent heat capacity. Okay? Specific latent heat. How did they phrase it in here? Yeah, specific latent heat, not capacity. That's why it's not a C. There we go. So, adding energy still. We got Q. Okay? The more mass we add, the more heat, or the more mass we have, the more heat we need. So it's going to be directly proportional to mass still. The thing that's going to be changing here, instead of having the delta T and C, we're looking at a different constant. All right, there is some constant that determines how much heat it's going to be taking based on how much mass you have for a particular material. Okay, and latent, if we're looking at like what that word means, latent means hidden. Okay, or like secret. Okay, so if you're like adding energy into this thing and you're just seeing nothing happening to the temperature, like I'm giving this thing energy, I've got it over a Bunsen burner, why isn't it changing temperature? That's why it's called latent heat, because it's hidden energy. Where's it going? It's going into separating those particles out, into turning it from a solid to a liquid, or a liquid to a gas. Okay, so specific latent heat, we got an L in there now. We're going to use an L for that symbol. Okay, so latent heat, that is a constant for any particular material, and it's specifically looking at a constant while it is going from a solid to a liquid or a liquid to a gas. Okay, if you're going from a solid to a liquid, they call it the latent heat of fusion. And what did they, I always forget that, oh yeah, duh. And then when it's going from a liquid to a gas, then they call it latent heat of vaporization instead. Okay, but for any of these, we can figure out our unit. Right? We got heat, measured in joules, amount of energy we're putting in or taking out. So latent heat, we need to get joules. We've got kilograms here. Okay, so this will be measured in joules per kilogram. Okay, don't have to worry about temperature measurements there because the temperature is being maintained the entire time. Okay, anything else left on the notes? Yes. Okay, so you are going to have to find in some like energies and like temperatures and stuff. Some of the problems we're going to be using on today's thing involve adding energy by running a current through something. Okay, so we're still just adding energy. It's just coming from, instead of like a Bunsen burner, it's coming from just moving electricity through something. All right, so let's think about a couple formulas that we saw last year. Okay, so a lot of these problems will tell you like how long something was on a Bunsen burner. Okay, but if you're looking at this equation, or if you're looking at this Q equals Cm delta T, or the Q equals mL, there's no time in it anywhere, right? So one thing that does relate to time is a quantity that we haven't talked about since last semester, and that's power, right? Because power is just the work you're doing over time, measured in watts or joules per second or horsepower, okay? The W there, work, is how much heat we're adding to it. When you're doing work on something, you're adding energy to it. All right, so work, another form of energy, heat, another form of energy. In this case, they are the same thing. Okay, so when it starts mentioning time, we want to think about power. Okay, so power would just be this thing over time. Okay, it would be Cm delta T over the time taken, okay? But we are going to need to find power. None of the problems you're going to be getting on today's sheet are going to be mentioning like this is how many watts it's taking. Instead, they're going to tell you like how much current we're running through or how much voltage we have, okay? So remembering back to when we were doing Ohm's law, okay? One of the ways that we had to find power was that power is equal to your current times your voltage, okay? So for a lot of these, it's going to tell you how much current you're running through, how much voltage you've got. Find out your power that way, and then if you just multiply that power by time, now you've got your energy, and now you can use the new Okay, so do keep these two in mind because they will be useful for today's stuff. Okay, but for solving stuff, we've got an equation. Moving it around, find things. Maybe some conversions for like Celsius and Kelvin. We've got a formula for that too. All right. A lot of this should seem kind of similar, like the CM delta T. I'm sure that Jennings did it because I did it, and I'm lazier than him. So he might not have done the Q equals ML one. Usually when we're talking about heat being added, we're looking at it changing, like not when it's changing between states of matter. But good to go. See you later.